You're involved in very risky business, and this becomes a big bone of contention for many people, that we, on the one hand, need to do what we need to do to make the products we make, but we have all this inherent hazard. And there's a large number of compounds that are currently in commerce that we know nothing about. So that simple notion of risk is a function of hazard and exposure is a big issue. So I want to turn our attention in the next two talks. This one is about all the other stuff, and I've teed this up to a certain extent. The second talk is really about energy. And I have recently begun to talk and ask people to focus on what I would call the forgotten principles. The last two and the first around around waste, and the last two around designing out hazard from a molecule have captured most of the attention in the green chemistry community. This idea that we do chemistry and we have a bunch of other things in the reaction, and those things are really important, is not one that you typically will hear from chemists when they gather, true chemists, when they gather to talk about chemistry, okay? So again, general background, I want to talk about solvents. By way of disclosure, I've spent an enormous amount of my time in GlaxoSmithKline focusing on solvents and trying to tee up to the pharmaceutical industry that this was a bigger problem than what they thought it was. And then we'll talk a little bit about solvent alternatives. So the principle is about auxiliary substances. It's beyond solvents. Okay, later on this afternoon we'll talk about protecting agents and things like that, but separation agents and solvents were what were given as an example. So that we're really going to just talk about those two things in this particular talk. So made unnecessary, so there's been a lot of effort in green chemistry laboratories to talk about solventless reactions or reactions in supercritical CO2 or in water, okay, as to try and say, do it unnecessary, or solid state. There are a few groups that just look at ball milling. That is, you throw a bunch of dry powders into a ball mill with some beads, and you run that at a high rate of speed, and you can actually get chemical reactions to take place in the absence of solvent. So there are strategies that people have used. And then the second one, innocuous when used. Now, I review a lot of papers for journals like Green Chemistry and Organic Process Research and Development and similar publications. And practically every single article I review, they ignore solvents. And academics are still using solvents, which industry has gotten out of 10 or more years ago. And I keep asking myself, why is that the case? And what I have come to discover is that there's an institutionalized bias against green chemistry. In other words, you have to replicate reactions using similar conditions, otherwise they don't think it's a legitimate new reaction, which again is kind of ridiculous in my opinion. I'd like to make sure that you know how important solvents are and all these other things like acids and bases, because if you look at how acids and bases are used in synthetic organic chemistry, we basically don't recycle them, and we use a lot of them, and they become a major issue. And talk about a few strategies. So the message is in the medium. And I will say this multiple times through this talk. Solvents matter. You can make better choices and still do the chemistry. In other words, if you choose an alcohol, choose something other than methanol, particularly if you're doing an aqueous quench. All right, use a higher molecular weight alcohol, which does not have the miscibility in water. There's lots of strategies like that that will enable you to run your reaction, not have any problems, and end up with a lot less waste. This is just a graphic a general graphic showing you solvent usage, and you can see that certainly coatings and industries and coatings and adhesives and inks, largest consumer of solvents, and that's just really as a vehicle of delivery. So this is why the car industry has gone into powder coatings. The aerospace and defense industry has gone into powder-based coatings if they can, because solvents play a huge role, and they generate either aqueous-based waste or air emissions. We still use a tremendous amount of hydrocarbons, less by oxygenated and still using chlorinated, but you can see that we've done a great job at removing chlorinated organics, except again in academic laboratories, okay, where they're still used just as often as benzene and a bunch of other compounds that we shouldn't be using as solvents. The world, I'm going to say this in energy, I'll say it here, the world is addicted to petroleum, and it's easy to use and it's cheap, okay, from economic standpoint. But we have to come to terms with that because these are not really very good solvents at the end of the day. Historically, in most industries, like I said, because of E factor, and Roger Sheldon's pointing out those facts in the early 90s, everyone focuses on waste. What this is just showing you is that in terms of the mass of waste, kilo per kilo of product, solvents account for the greatest amount of waste in batch chemical processing. Again, not in petrochemical so much, but in batch chemical operations. And the cumulative mass going to waste after solvent and recovery, so these are reactants, and this is solvents, and this is other. So if you're in a business and you're saying, I want to reduce my mass intensity, or I want to reduce my E factor, what am I going to go after? It's going to be solvents. So hopefully when you go back to labs, if you're a synthetic organic chemist, I hope you'll begin to think more mindfully about solvent and solvent uses. They're critically important. In batch chemical operations, there are some real significant challenges, all right? Complex target molecules, you saw some of the ones that Rich put up there a few moments ago. High molecular weight, highly functionalized molecules. They're lipophilic, that is, they dissolve in fats. So we have to use certain kinds of solvents to make sure that they dissolve. We have a large number of reagents and reactants that oftentimes we don't pay much attention to. Synthetic routes, okay, 7+ stages to get to the desired product, all right? And the waste accumulates through each of those stages. And then this mixed aqueous and organic waste is a real problem. What do we do with it? In pharma, they burn it. So you lose the value of the solvent, and you have to add BTUs to burn it. And the result is a lot of air emissions of one kind or another. Now, obviously, they try and reduce the nasty things coming out of there, but the one thing that they're not recovering is CO2. And in case you didn't know, we have a problem in the world with CO2. So for a typical pharma process, and I would say for most batch chemical processes like this, 6+ stages, 13 kilos per kilo out of a total of 16 is solvent. And the thing that no one pays attention to typically, again, we're focused on yields. We might worry about how much solvent we use for reaction, but no one pays attention to how much we use for workup. That is isolation. So we'll wash something 6 times with, cold solvent or something like that. What the heck? It's only solvent. And we just pour it in the waste can and we're done with it, right? So huge amount is just used for product isolation, and that's something that we need to change. From product separation isolation, largest contributors to capital and operating expense and processing time. Processing time is extremely important. Time is money. And so if you have to manage those solvents in your process, it's costing you money. So again, solvents are not your friend. The other factoid I will give you is that we typically run reactions extremely dilute. And for the life of me, I can't figure out why, but we do. if they're 10%, that's a lot. So there aren't enough people paying attention to product or process intensification. That is running these things at higher mass relative to the solvent, right? Higher concentrations. There's lots of reasons why we perhaps don't do that. One is mixing. The other is control of exotherms or endotherms. And that's really the only reason to use the solvents typically. So this just shows you that in a typical pharma company, and I could go to any pharma company and replicate this in most other batch operations, but they'll focus on a few solvents or a few classes of solvents. And these ones that are in red are actually, they have R64 phrase, which is a safety phrase, which you want to stay out of. The rest of these are not so bad. They all have issues, but it just gives you a sense that there are just, typically you are faced with maybe 20 different solvents. You probably can run most of your reactions in 5. People just don't try it. You go to the literature, you find that somebody ran it in some solvent, and you just replicate that. And my question is why? Why do you do that? Why do you have to? Because it's there. That's the only answer I can come up with. So we know that they're used for reactions, for solvent extractions, azeotropic distillations, cooling, precipitation, washing, mixing. All those things, that's why we use solvents. But again, the question is, how many of you look at mechanistic kinetics to understand how you have to mix it, how long you have to heat or cool, so on and so forth? Very few of you. You just run the protocol. You don't think about the mechanism and how long things do. You set the reaction up, you run it overnight, so the protocol becomes you ran the reaction for 8 hours or 12 hours, when it actually was done in the first 3 minutes. So solvent effects solvents play an enormous role, and it's always been curious to me why chemists don't think that solvents actually play a role in the reactions. But they do. There's specific chemical reactions many times that they support the reaction. There's solvation effects either in the reactants or in the product that are taking place. And there's a lot of things around polarity changes that solvents enhance. So again, this is, in my estimation, something that chemists don't pay enough attention to, is how the solvent is actually promoting or inhibiting the reaction. And typically what you'll find is a chemist, if they end up with a yield, say 80% yield, they'll go and look for another chemistry. The engineer will go after mixing or heat and mass transfer or a different type of reactor and possibly get that yield up to 90+%. The question is, why are chemists so quick to change their chemistry and not use some more engineering in what they do? So solvent selection is extremely important. You can look at reaction types and process, so on and so forth. You can evaluate it experimentally. You need to refine it. Again, solvent choice is extremely important, and the days of saying we don't know which solvent to use are over. There are so many tools nowadays around solvent selection that you all have access to and you should all be using on a regular basis if you're doing synthetic organic chemistry. This is an example of a guide that we created in GlaxoSmithKline. It was reduced down to a single page. What I say is it's simple but not simplistic. There is an enormous amount of data behind this particular graphic. It was organized by class of solvent, and the top solvent was the best, this being the worst. And it was across a number of different impact categories. So there's waste, environmental impact, that's environmental waste, environmental impact, health, safety, and life cycle. So we did a life cycle of all of the solvents. And what I can say, again, it's a multivariate problem, right? You can see that depending on the solvent, they have different effects. So down here when you're into ketones, there's a tremendous life cycle issue because you're taking petroleum and you're functionizing, you're putting an oxygen on a reduced molecule. That takes energy. And it's also very wasteful. So, solubility of your product and your precursors, viscosity, concentration, kinetics and thermodynamics, and thermal conductivity and exotherm control. That's what you need to pay attention to. These are process metrics that we found to be very useful, and I won't go into them, but the point is, again, multiple metrics. They tell you a different story, okay? And what you want to do is to find the best combination of all these features. So what about all these other things like acids and bases and salts? How many of you salt out something? How many of you play with ionic strength to get the molecule that you want? And what this is showing you here is common chemicals and the extent to which they're used. Again, top 100 materials or reagents that were used. Just to give you an idea, again, simple things like hydrochloric acid, sodium hydroxide, and salt, sodium chloride, top used chemicals. All right? They aren't exotic materials. So here are some options for solvents. Like I said, pay attention to solvents and some strategies. So recycle and reuse. I'm not sure how many people are doing that. No solvent, how many are investigating that? Alternative. I don't have ionic liquids here. I'm not a big fan of ionic liquids for a variety of reasons, but they are being looked at as alternative solvents. Benign or less toxic is the reason that ionic solvents have an issue. There are many things around volatile organic solvents, so again, avoid the use, come up with something that's environmentally benign. The reason we like to use very volatile solvents is that they are easy to separate. And the reason that we like ionic liquids is zero volatility, a single measure typically. And again, when you look at multiple measures, they don't really cut it. Solvent-free reactions, I talked about milling and grinding. Catalyst-supported reagents, there's liquid gas. Again, lots of different strategies that are being investigated. Same kind of thing. From a macro scale, so plant design all the way down to quantum mechanical and nanotype scales. There's much you can do with technology to improve reactivity. All right? Going from a macro scale reactor, say a 10-liter, down to a micro scale, like HPLC tube that you run the reaction in a micro reactor. Actually, many of those reactions, great for controlling exotherms, great for using highly hazardous materials, and producing a lot of product in a very short period of time. But again, we typically are not trained. We're trained using beakers and round-bottom flasks and other things. So in the future, we want to get to using different things. Water has been investigated tremendously, and if you go to many green chemistry conferences, you'll see lots of reactions that have been demonstrated in water. The other one I like is actually designer solvents. This actually comes back from, or started in the 1990s, late 1990s at MIT, but where they investigated functionalizing molecules and noticing the difference that it would have on the reaction. And again, tailoring the molecule to the reaction. The problem with this is it's very time-consuming to do that. And then you're in the game of infinitely tailoring your solvents. Carbon dioxide, as I mentioned, is used quite a bit. There are issues associated with energy with this and with solubility. Lots of reasons for using it. There's lots of CO2 available. Chemically pure, resistant to oxidation. It's a great solvent for running hydrogenations because you're already at high pressure, and dropping in a catalyst is pretty easy. So great use of supercritical CO2. So I hope that I've convinced you that solvents are an extremely important part of synthetic organic chemistry. It isn't just A plus B going to C. All right? Huge effect on environmental life cycle impacts. So we haven't talked about life cycle, but that's looking at environmental impacts from raw material extraction all the way through end-of-life considerations. It's an extremely useful methodology for helping you to understand your choices that you're making in the chemistry. And very few people are being trained in life cycle and know how to use it. There's lots of tools, as I mentioned, for solvent replacement. You don't have any excuses not to pay attention to this, all right? So I'm looking forward to the day when I review, when everyone has got that. And again, lots of solvent replacements are available. So I'm getting the high sign here that I have to move on. And we can take questions